I'm going to be presenting a paper by several of the people at the workshop, including Maxwell and Chris and other people from our lab. I've already introduced myself, but just in case, my name is Mahault Albarracin. We're going to delve again into active inference. I think we're going to hone in on some issues that Maxwell definitely introduced. We're going to basically argue that active inference is uniquely suited for engineering ecosystems. So, as you saw from Maxwell's presentation, active inference is grounded in physics and it leverages Bayesian inference. We're going to touch very vaguely on this, but since he went in depth into this, I won't go too much. We're going to start with an outline of the vision for research towards network collective intelligence, the hyper-spatial web of AI, which is the key goal of Verses. And we're going to argue that active inference is the most suitable approach for this aim. It's a first principles approach, it's inspired from nature, it's inspired from neuroscience, it's physics-based, and it basically allows us to formalize the basic properties of intelligence. In the third section, we're going to try and talk about model evidence a little bit more and how it relates to perception, learning, and action. We're going to focus on the role of communication and shared languages and how this can be enabled through the propagation on a factor graph. Then in the fifth section, we're going to talk about the ethical considerations, the perspective on aligned and ethical AI, the value of diversity and individuality, all of this properly captured through active inference. So, this is the cover of a book that was written by our CEO, Gabriel René. And basically in it, he lays out a vision for the future of AI research through the hyperspatial web, which is interconnected intelligence. So rather than just brains in a silo, we're talking about intricate ecosystems where intelligences interact in real time and they form emergent superordinate scales of intelligence. The nodes in the ecosystem could be human, they can be human-designed artifacts that embody intelligence. So here, basically, what we're arguing is that the zenith of AI may be this distributed network of intelligent system, rather than some kind of monotheistic vision of artificial general intelligence or artificial superintelligence, which is generally just this one entity. Here, the active inference allows us to use an approach that is universally applicable because it's based on first principles of physics. It gives us it uses the laws of the universe to make a foundation for intelligent systems. It also leverages, as Maxwell said, the statistical and probabilistic tools which are essential for decision making and learning in an optimal fashion. Here, through this approach, we design a toolkit. And this toolkit gives us interaction, learning, evolution within a network. Sorry about that. And the dynamics of sparsely coupled systems can be written this way. Through active inference, we understand that they can self-organize at several scales. It takes into account the physicality of information and its processing at every scale. It enables AI to scale in the way that nature does, which aggregates individual intelligences within and across ecosystems. So, I'm going to go very fast through this, because again, this is a lot of what Maxwell covered. We know that for a long time, AI was mostly inspired by neuroscience. So for instance, the Michael-Pitts neuron to deep learning architectures were all mostly based on what we understood of the brain, and the more we understood of the brain, the more our definition of intelligence changes, and therefore the definition of AI changes. However, we do think, as Maxwell showed, that intelligence isn't internal, it's not constrained to the brain. And in general, it's not only a human property, it's ubiquitous in natural systems. It manifests at various forms, like colonies of slime molds that can solve mathematical problems. So we're arguing for a shift from a neuroscience-centric view to a more holistic understanding of intelligence. This approach will allow us to not just how intelligence appears to researchers, but what it is fundamentally through more of a process approach. So if we apply this Bayesian, these Bayesian principles to machine learning, we have a more comprehensive understanding of intelligence that's not just descriptive, but explanatory. We can find the roots of this approach in the cybernetics movement of the 1940s. They aim to describe the general properties of regulatory system. It gave us principles like feedback, homeostasis, the good regulator theorem. And so contemporary developments of statistical mechanics, particularly in the far from equilibrium systems, have allowed us to formalize these early insights into a physics of self-organization. So Maxwell, Dalton, and others, and there's so many others, so I'll be saying and others a lot, but do read the papers, they're good papers, have introduced Bayesian mechanics as a framework that can describe or simulate intelligence systems. They emphasize that the physical implementation is the ultimate constraint on all forms of engineered intelligence. So this is hearkening back to questions we were having earlier on the relationship between information and matters. To do so, we use Landauer's principle, which states that there is an energy cost to irreversibly read or write any information to a physical medium. It underscores the importance of considering the physicality of information at every scale of self-organization. And this ties again to some conversations we were having earlier with Adam about the different configurations that may be more or less conducive to certain kinds of processes at different scales. So, through active inference, we can thus write down the dynamics of those sparsely coupled systems through a formal definition, which basically define intelligence as the capacity of systems to generate evidence for their existence. And we can see how that's profoundly related to the physical constraints. They encompass cognition, problem solving, and sometimes even creativity. So active inference is a very versatile tool, and it can be applied across various domains from neuroscience to AI and robotics. So we call this self-evidencing. Active inference introduces the concept here of model evidence, which is a scalar value that quantifies the degree to which observations conform to the generative model. The model evidence serves as the sole optimization criterion. So we can extend this formalism to collective intelligence, which give us a mathematical theory that it can apply at any scale, so it's completely scale-free from rocks, okay, I'm so sorry, to rock stars. You're welcome. So this nested recursive approach to existence allows us for a very unified theory of intelligence that is rooted in physics. So importantly, the formalism here incorporates the principle of Occam's razor. It mandates an accurate, yet minimally complex account of sensory exchanges with the world. It serves to limit overfitting and poor generalizations in intelligent systems. So for those of you who are most interested potentially in machine learning and what kinds of issues you might find with problems of machine learning, the key term here is limiting overfitting through the natural process of active inference. So the concept of model evidence is operationalized through belief updating at several scales. We come back here to inference learning and model selection. In the realm of perception, active inference is updating variables to align with observational data. So for instance, you navigate through a dark room, which involves sensory inputs like touch to update beliefs about the environment. Learning in active inference involves updating parameters to maximize model evidence. It's like understanding that you're in a room with the elephant based on the accumulated sensory data. And then there's action selection, which is geared towards maximizing the expected model evidence through the Bayesian mechanics that we introduced, such as, for instance, leaving the room because there shouldn't be an elephant there. The approach captures dual aspects of Bayes optimality, which favors choices that ensure the greatest resolution of uncertainty while realizing preferred outcomes. So, Bayes optimality, greatest resolution of uncertainty, realizing preferred outcome. So we have a balance between information and preference-seeking behavior, which leads to emergent properties like the curiosity we discussed earlier. So here we have a calculus for movement in the space of beliefs, which align the principles of natural design and potentially next generation AI systems. So this is effectively a paradigm shift because we're emphasizing the importance of belief update, which is not adversarial, but integrative. It formally relates to state-of-the-art approaches like neural networks. It has been shown that all canonical neural networks minimize their free energy, which showcases the strength of these approaches and enables cross-pollination and refinements in AI. So, if belief updating is movement in a statistical manifold, each point on this manifold can correspond to a probability distribution, and messages must be sufficient statistics or parameters of these distributions. So this is how we introduce the concept of precision, or inverse variance, which quantifies the confidence associated with any variable drawn from a distribution. And again, this is pretty key. This is something we don't necessarily have in other kinds of systems. So, active inference uniquely addresses various types of uncertainty, such as irreducible noise, ambiguity, model noise. Non-probabilistic approaches, for instance, can fail to quantify these uncertainties, but through active inference we can, and it makes it more robust and more reliable. Hi. Hi. And this is important for things like structured learning or Bayesian model comparison, through which we can potentially go from the most basic model to a model particularly tailored to any problem you may have in front of you. One of the most compelling approaches, aspects of active inference is its approach to managing complexity. So for instance, we can add predictive accuracy and complexity on, and we can put them on an equal footing with complexity, which is crucial to automatically finesse many problems with machine learning schemes that focus solely on accuracy. We encourage, through this framework, a model that finds parsimonious explanations of observations, abstracting away from useless details, and again, not necessarily overfitting. Active inference thus provides a good framework for learning representations in which distinct generative factors are disentangled. And the low-dimensional disentangled representations are not just useful for an AI system itself, but are also more explainable, more human interpretable than generic latent representations. So while traditional AI emphasizes parameter optimization, here we have the main computational task to be marginalization. So mathematical techniques like variational inference to convert this complex problem, make it into a tractable optimization problem. So in the realm of machine learning, active inference introduces the term information gain, derived from model evidence. We can redefine the concept of a reward in Bayesian reinforcement learning. It moves away from a single outcome optimization problem to a multiple constraint satisfaction problem. It aligns more closely with natural systems, and it provides a more normative theory for learning. So rather than focusing on maximizing rewards, active inference generalizes the notion of rewards and labels every encountered outcome in terms of how likely it is that this would happen to me. This moves our understanding of intelligence away from monothematic reward optimization towards multiple constraint satisfaction problem. And we can deal with much more complex issues and potentially generalize better as well. It has a more holistic approach to AI, which goes from big data to smart data. It has important implications for hardware and energy efficiency, because if you can be more frugal, you don't have to consume as much anymore. Can be implemented with biomimetic efficiency without the need for traditional GPU-based high-performance computing, although this is still an ongoing problem. So now we get to the role of communication and shared languages. We see throughout most systems that it's pretty pivotal. In the biblical story of the Tower of Babel, we can see that the metaphor serves for the chaos that ensues when a common language is disrupted, leading to misunderstandings and the collapse of collective endeavors. And so through natural languages, we can express ourselves, but they have limitations, especially when serving as shared human-machine language. The serialization of thought into discrete tokens is essential for sparsity structure, but it may not be the most efficient form of information transfer. So we propose that shared generative models and communication protocols for intelligence at any scale are important. They could be shared external store of knowledge or structured communication protocol that acts as a sort of lingua franca. Such a framework would enable AI agents to offload tasks to other, more specialized agents, for instance. So here, intelligence as self-evidencing, as you saw earlier, is inherently perspectival. It involves actively making sense of and engaging with the world from a specific point of view. And this is crucial for developing AI systems that can work in harmony, sharing information and tasks seamlessly, but also maximizing the kinds of information they bring to a common ground. So how can we communicate? Well, we propose that factor graphs may serve as the right framework for representing complex systems in terms of their constituent factors. These graphs are a special kind of network, where nodes, again, correspond to the factors of Bayesian belief or probability distribution. They enable message passing, and they allow for updating of beliefs across the network. And you can see how this would be crucial for distributed intelligence, where subsystems would need to coordinate and update their understanding of the world. It has an interesting aspect. The nodes of a vast graph can be partitioned into smaller subgraphs, each corresponding to an agent updating its beliefs via internal message passing propagation. So external messages would correspond to communication and belief sharing that rest upon certain factors being distributed or duplicated over two or more subgraphs. This is how you maximize the possibility of theory of mind. So through this, we have a sort of formal way, a formal account of collective intelligence, and we can establish a common language and a protocol which enables steps towards an ecosystem of naturally occurring and artificial intelligence through the emergence of what enables the theory of mind. There's extant work in the field that's consonant with the extension of this in multi-scale intelligence, including complex internal structure of LSTM cells, the repetition of split transform, merge strategy across scales in the ResNext architecture, capsule networks, and 1,000 brain theories. We also propose that because all of these agents have to be perspectival, spatial addressing is a crucial component of the development of intelligent systems. So when we aim for the network of distributed, emergent, shared intelligence, we need, for instance, in the brain, neuronal populations that receive spatially addressed inputs from other parts of the brain, which allows for effective communication and function. This is one of the concepts that's being developed by the IEEE P2874 Spatial Web Working Group. We're gonna have to find a better name for this. Basically the group is working on creating open standards for spatial messaging, passing protocols, and modeling languages. Obviously, if you want to attend such meetings, you're welcome to. They're open, and they take feedback from community, and it's valued feedback. These protocols are the first step towards realizing the kinds of distributed intelligence we're talking about. They include, for instance, an irreducible spatial addressing system, which means that the addressing is fundamental and cannot be simplified further, which kind of harkens to compression and minimal description length, one of the potential key aspects, in fact, of degrees of consciousness. It's essential for creating robust and scalable networks of intelligence agents. So, the protocols would enable the systems to identify themselves in relation to shared factors and declare their origin. This will allow us to determine how they can work in harmony, which share information, sharing tasks, and understanding their potential outcomes. If we scale these protocols or pull them into pragmatics, we get to shared narratives, shared goals. We have nested intelligences, which means that we aggregate individual intelligences and their locally contextualized knowledge within and across the ecosystems. We're not just adding more data or layers. Here we have emergence in terms of sharing aspects of the same generative model. So, these are the steps towards developing a hyperspatial modeling language and transaction protocol such that such narratives can emerge. Now, what are the ethical dimensions? When we're talking about this, we usually talk about AI alignment, and we're focusing on what it might mean for sympathetic intelligence to help us with AI alignment and the challenge of bias. We all think AI alignment is a critical issue, which again aims to align AI system values with the human values, especially when considering the potential for AI to achieve superintelligence. But as you saw, if everything is perspectival, so should your alignment be. It's part of the ability of AI agents to share aspects of their generative model, but also enables them to, again, coordinates relative to the parts of the alignment they wish to enact. In general, AI systems are black boxes, which limits their transparency, their explainability, their auditability. And through this, we can perpetuate biases, and we can build on discriminatory data, which sustain social biases and perform harmful practices. So it's not just a technical problem. It also requires us to understand social policies, government regulations, ethical norms, and bake them into how we understand perspective. So here we could see how this system would have nodes and layers that enables a kind of collective self-monitoring and self-organization of salience. But we must thus address questions such as authority and power, and how, when deployed at an industrial scale in commercial settings, these might have crucial impacts over larger scales. We also emphasize the intrinsic value of individuals. This is related to the discussion we wish to have earlier, where each person has a distinct and unique life experience, a perspective. This uniqueness is not just a philosophical point of view, it's a practical one. Each individual knows something that no one else does. This diversity of perspectives is not just beneficial, it's essential for the form of collective intelligence we're envisioning. It's not the kind of intelligence seen in eusocial insects, where most individuals are replaceable copies of one another. It's not suitable for systems where individuals and nodes embody complex generative models that evolve over time into vastly differing versions. This architecture must positively value and safeguard the individuality of people, as well as potentially non-human entities. It's an architectural necessity for the system to work. It works best when it incorporates these diversity. It allows to function optimally And especially, it's useful in special cases of functional specialization across the components of a complex system. So we can end this presentation, wow, on time too, damn, on the developmental stages and implementation plans for active inference AI. So we propose a multi-stage developmental plan for AI technologies through a roadmap by technology readiness levels. This is the kind of framework used by institutions like the European Commission, the ISO, and NASA. So we consider that we are currently at S0, which is systemic intelligence. It's the current state of AI. It has a universal function approximation. It maps from input states to output states while optimizing a well-defined value function. We can think of deep learning, Bayesian reinforcement learning. Well, we want to move to sentient intelligence, for which we believe we're getting closer. It's not properly achieved, but we're getting closer.
Some specific definition of sentient, which might not be...
Sure, precisely. So this stage will involve active inference based on belief updating and propagation. And it's responsive to sensory impression and focuses on planning as inference. So this is the definition by which we understand sentient here. It maximizes expected information gain and value, which are part of the generative model. It's information seeking and preference seeking. But we don't want to stop there. That's not the end goal. We were talking about shared. So the path to shared is sophisticated, in which an extension of sentient focuses on the consequences of actions for beliefs about states of the world. So I'm not just focusing on a policy over time, I'm focusing on what might be my belief once I reach a certain kind of outcome. It uses generative models with discrete states and is amenable to modal logic, quantum computation, and category theory. Then we move to sympathetic, which I mentioned earlier, where we would recognize the nature and dispositions of users and other AI. It recognizes and instantiates attentional and dispositional states of self. So it has the capacity for theory of mind. It can take the perspective of its users and interaction of partners. We already have certain models that have the beginnings of this, but we are nowhere near the extent to which we would need to be. So this is so far aspirational. And then the goal, shared intelligence, where a collective intelligence emerges from the coordination of sympathetic intelligence and their interaction with partners or users. And this emerges from dense interaction between agents networked into a hyper-spatial web. It corresponds to artificial superintelligence, but no longer as a sort of monotheistic entity. It's believed to be more distributed and potentially even, let's say, planetary scale, but why stop there, right? It could be anywhere from cosmos. So it's important to say that these stages are not necessarily sequential. They can sort of evolve in parallel, but the benefits of each stage, which are at different levels of progression, will benefit the next ones and improve their velocity. So, we've discussed the importance of multi-scale networked intelligence as the ultimate goal for development of AI. We've talked about Bayesian mechanics that allow the system to adapt and learn in a way that's aligned with human intelligence. We think that shared intelligence will emerge from the interaction of intelligences networked through this hyperspatial web, which includes natural and synthetic forms of intelligence. It will be aligned with time-tested methods and design principles observed in nature. So yeah, thank you, and thank you to the co-authors on this paper. And I don't have to take them, by the way. The other, go for it, yeah.
Yeah, so you mentioned the Landauer limit as a sort of having some relation to active inference, but I didn't quite follow the correspondence. Is that encoded somewhere in the equations?
Maxwell, do you want to take that one? Landauer principle, why?
Sorry?
Why is the Landauer principle important, and why does it relate to active inference?
So, who knows what Landauer's principle is? Okay. So Landauer's principle is one of these equivalence relations. I'm sure everyone's heard of E equals mc squared, right? This means that mass is equivalent to energy. And more recently, over the last 10 years, a new equivalence equivalence principle was experimentally verified. This is Landauer's principle, which basically tells us that information is physically real, and that reading and writing bits to a computational substrate necessarily incurs a thermodynamic per bit cost.
Erasing.
Yeah. Yep, sorry. It's a brain fog. I'm sorry. Yeah, I'm trying to make sense. So, yeah, the Landauer's principle is, I mean, it tells us that information isn't just this feature of our descriptions of systems, like as Raf, you were just saying, it's when you delete information that heat is released. Experimentally, we know this is the case because if you bring a computing system very close to absolute zero, and you delete a bit of information, it releases heat. So and the free energy principle is all about this connection between,
read and write and the boundary, in which case the cost of reading and writing information and potentially changing information has a physical limit.
Right, so my question is there some correspondence established in the literature between the sort of communication or structure of a network in active inference and the bitwise costs under Landauer's principle, or are these just two sort of frameworks that talk about the same thing? You know what I'm asking?
Yeah, has it been established in literature?
So the quantum, one thing that I didn't talk about because it would have taken another 30 minutes is that there's a new formulation of the free energy principle that is not multi-scale but scale-free, and it's based on quantum information theory, and that ties directly into Landauer's principle. So in that version of the free energy principle, what you have is, again, a per bit or per nat cost for the erasure of information.
Yeah, I mean, I have a hot take on this like, yeah, I don't know, it's probably not a good, like, point to do it, but
Too late, go for it.
yeah, so I think he kind of like incur the cost, he kind of like incur the basically some sort of chaos divergence cost on like belief updating, like Ortega-Brown type of bounded rationality, like kind of like cost on like cognition. Like you get the same terms from like Landauer limit. You get the same terms in econ under the, but you get the same terms, it's like in econ literature, it's known as a theory of rational inattention. Yeah, my take, like why this? It's not because like managers in corporations are like exactly bottlenecked by like Landauer limit, but it's basically because chaos divergence is the most natural way how to measure distance in cognition. So basically, if you do something like a perturbative expansion of any cognitive cost, like the first term will be chaos divergence. So this is kind of originating in like how we model bounded rationality, but it's not the case that the Landauer, like the Landauer limit would like directly say something about like how managers like read like central bank reports. Yeah, so it's side note.
Oh yeah, I mean, I think maybe this is a whole other rabbit hole, but I think there's an underlying question here of active inference and the free energy principle as a description of systems, and active inference as an engineering approach for physically inspired agent systems and models of business that have models and so on, right? Where the Landauer principle, I mean, if you're approaching the actual thermodynamic Landauer principle, I want to talk to you because you have some tech that I don't.
I mean, that's why Chris Fields can leverage it, right, at the level of quantum physics, but beyond that, it's like, well, okay, well, we may not be there, but in effect, it does speak to this physical limitation of information sharing, and if we can go all the way to what Chris Field proposes, eventually we'll have something extremely precise, and potentially the formulations of something that resembles like an actual theory of like, you know, the breaking apart of the mind-body duality, which is something that Maxwell has worked on quite a bit, and I hinted at during his presentation as well. I think you were trying to say something.
Honestly, I lost my thought.
No worries. Okay.
I'm so sorry, I'm super foggy.
I think there was your hand, yeah.
If I understand correctly, this, like I implies turning, for example, businesses into those cognitive models. Like you take the cognitive complexity of some business corporation and translate it into executable version, right?
I suppose you could do it with a business. I guess we were thinking more along the lines of any kind of regroupment of intelligent entities. So it could be just this, group here. It could be animals that share information. It could be a corporation with a more strict structure, less hierarchical. So yeah, I guess it could apply to business. Yeah, could apply to business. I think there was a follow-up. Yeah. Did you want to finish that? It felt like you had something else to say.
Yeah, so, well, practically speaking, I don't think we're going to, write generative model for like small community or family because nobody's going to do this, and this is not probably what is needed. But for, let's say, business, yes, ecosystem may be a good example because it will improve
Efficiency.
like how we track the total health of the ecosystems in general, but returning to the businesses. And so the problem that I see is that the complexity, actual complexity, is perhaps very, very high. I think much higher than complexity of the mind. Like this is what you mentioned as sympathetic intelligence. As far as I understand, you on that level you assume that we untangle the theory of mind basically on some fine grained level, so we can, or not we, but AI can relate and like model appropriately. But I think large businesses are much more complex than a mind. Even though people say, "Oh, mind is so complex," I think businesses are much more complex. Even if the fact that they're based on people and people relations, this of course makes them practically even more complex, but even if you try to abstract and reduce humans just to functions, like complexity of the businesses such as, I don't know, Google or TSMC, I think it's just enormous. So.
See, but this is beautiful because it could apply to why can you understand the business, why can anyone? And
nobody can understand this.
Well, some people do, and the reason that they do is because there are constraints. There are rules.
Not a single person understands them.
No, not a single person, but effectively nobody understands culture, yet you can act within it because the culture has places limitations on the kinds of things you can do. And so you could effectively translate, if you wanted to do it manually, of course, you could translate certain kinds of rules, the purposes, the connections among different actors and how information is passed across these different actors. And in general, most successful businesses have put their processes into some kind of predictable outcome. So like there's something written out. There are meetings that concern different kinds of information. You can cast this as information passing or belief updating for specific kinds of factors. And then you can predict the frequency at which this is done. So there's a way to cast it. But if we did, when we do succeed at understanding structure learning, we won't even have to. We won't have to do it manually. We can just encode the baseline and let the system figure out its own structure and then understand how it can optimally function based on that structure.
Well, but let me just throw another thing in there. I think there's an attitude. There's an attitude that you referred to a little bit there, but I want to make it a little bit more explicit, which is the notion of distributed intelligence, meaning to a large degree we actually don't have to have a complete, explicit, monolithic model of anything, and rather just leverage the way that intelligence actually already shows up in nature, which is distributed in artifacts and in processes, in models in the head, and models in computers, which might be inference models, or might be like effective little deterministic or logical models and so on. And so all these things can combine to act as the effective model for the whole thing, right? So when you talk about understanding business, it's not an atomic Bayesian understanding business necessarily, but it's the combination of all the
So you are using the notion of like shared generative model. Does it mean the, like, I don't know, us looking on the whole system of all the intelligences, and because I don't know, to what Max like complained about people using generative models to describe the models which are kind of in the minds of agents. So how we should use the terminology or something.
So I think the question is something like, if generative model is like the scientist model of the entire system, what do you mean by shared generative model?
I don't think the scientist is the shared model. I think the shared model is the overarching system organizes, and through this organization sort of nests a series of large-scale predictions or states or policies. Through the distribution of your understanding of a part of the puzzle, more evidence can be accrued for some higher level inference. It doesn't mean it's in the head of anyone's particular, or even in the head of anything. It's more, there are processes that testify to certain kinds of joint probabilities, which therefore testify to a generative model, or at least a series of nested generative models. You can always recast systems, and you can cast systems in terms of this group probably has currently a shared generative model of what happened, even though at the individual level you probably saw the talk a little bit differently, but if you had to aggregate your knowledge, you would come to some kind of aggregate state. So this is how we're generally talking about it.
So I think that the
Do you have a really strong preference to say the thing you want to say?
I think it will help.
Yeah.
So I argue that this is connected to like when Maxwell says that from a descriptive perspective of the free energy principle, as well, it describes a system that has that is described by a generative model, and then a part of that system which is an agent that contains a variational density that approximates that generative model. When we talk about sharing generative models here, in the sense of sharing the structures, code or data structures that encode factor graphs or whatever representation of a model, we're actually talking about these about sharing
Latent
variational posterior
states.
whose structure is assumed to be the same as the generative model, and therefore like you can substitute one for the other.
So if you're talking about the engineering, it could be a massive graph with subgraphs that share some.
That's not the question. The question is like if you are actually sharing the densities or.
Yeah.
Okay.
Okay.
Or at least the structure. I mean, it can go both ways. It can go a bunch of different ways. Right? It's an engineering question. Like my implementation does share the densities, but you can do a bunch of different things.
Cool. Thank you very much.
No worries.